Welcome to the presentation of our paper Incremental Learning of EMG-based control commands using Gaussian processes. In the following, I will give you a short overview of our approach and how we evaluated it within a user study. My name is Felix Schiel and I hope you enjoy the presentation. Measuring electrical potentials produced by muscles is referred to as electromyography, or short EMG. EMG interfaces can be used to command assistive devices in healthcare applications, for example, myoelectric prosthesis. In our lab, we developed a wheelchair with an attached robotic arm, which can be also controlled using an EMG interface. To convert the EMG signal into control commands, we are using as the underlying model the sparse Gaussian process approximation Variational Free Energy. For each dimension we would like to control, one sparse GP is defined. Pattern recognition in myoelectric control is a very challenging field, since the underlying distribution of the signal is likely to change during the application. Changes of the arm position, sweating, or different levels of muscular activation often lead to significant instability of the control signal. To overcome the challenges and to regain a satisfying performance, we propose an adaptive approach which updates the sparse GPs during runtime. The current slide visualizes the key parts of the adaptive model. New unlabeled incoming samples are first categorized if activity of the user is detected or not, and grouped in respective batches. Operating on batches increases the robustness against outliers. The data of the active batch is compared to already labeled data using metrics which measure the intraclass distance as well as the interclass distance. Based on the metrics and the computed output of the sparse GPs, update rules determine if a batch is used for an update and what the label of the batch should be. When a batch is eligible for an update, data points of the batch and the corresponding label are added to the dataset of the sparse GPs. If specific update rules are activated, also new inducing points can be added or their location can be optimized. Further details of the algorithm can be found in the paper and the supplementary material. To evaluate the adaptive model, an online user study was conducted. A 2D task on a screen was performed by 6 subjects using the EMG-based interface. Different arm positions and targets on the diagonals were used to evoke changes in the input data to challenge the robustness of the model. The subjects had to navigate to all targets once in position P1, in which also the training data was generated, and afterwards 2 times in position P2, which we call here P2 with 1 star and 2 stars. The experiment compares the performance of 3 different models. The first model is based on the sparse GP approximation FIT-C, which we have used in previous experiments and is therefore used as the baseline. The second model is based on the sparse GP approximation Variational Free Energy, and the third model is the novel adaptive model, which uses also the sparse GP approximation Variational Free Energy. The pilot study with 6 non-disabled subjects shows a significant increase in performance of the adaptive model over the non-adaptive models. In the study, diagonal navigation as well as change of the arm position confront the model with highly challenging conditions, which was handled reliably by our approach. Future work will include a long-term evaluation and extension of the approach to 3D, as well as testing with disabled subjects. Thank you very much for your attention. I hope you enjoyed the talk.